Okay, yeah. So this week we'll be talking about some string-related algorithms, and hopefully, hopefully everyone finds them interesting. So here's the link to the slides. Hopefully it works, and if it doesn't work, just let me know, and I'll take a look at the permissions. Okay, so I'll just leave that up there for a minute or so, just so everyone can get on the slides if they want to. Okay, I think that's good. So the first topic I'll be talking about today is polynomial hashing. So what is polynomial hashing? Well, the general idea is that we want to hash a string, and for every single string, we want to assign a unique integer value to it. And the good thing about doing this is that since comparing strings is O of n, where n is the length of the string, then this is much slower than comparing two integers, which is O of 1. So if we can somehow assign a unique integer value to a string, then comparing two strings would therefore become O of 1 instead of On. And this is much faster. And it would be very useful for a lot of problems that need faster runtime. And now the question we want to answer is, how do we find this unique integer? So we first choose two integers. We'll call one the base and then the others the modulo. And so here you can see that S is the string. So S0 is the first character, S1 is the second character, and then so on. And P here is the base. So what we essentially want to do is we want to calculate the integer value through this formula. So S0 plus S1 times the base plus S2 times the base squared until we get Sn minus 1 times the base to the n minus 1 power. And then we take this mod m. And S0 here, since that's actually a character, we're going to use the ASCII value for it. So if you're not familiar with ASCII values, that's every single character has a unique value in the ASCII table. So we'll be using that value to calculate our hash in this case. And then since we're taking modulo m, there's going to be collisions because there's only so many distinct integer values, and that is 0 to m minus 1. So to minimize the number of collisions, the modulo should be a large prime number. And often people use 10 to the 9 plus 7. So that's just an example of what people use. And this is how you calculate the hash value for a given string. And most of the time it will be unique, but there could be collisions, and I'll go over how to minimize those collisions. So here's the code or here's an example code for polynomial hashing. So you can probably realize why it's called polynomial hashing now, because it looks like a polynomial function where you're doing S0 plus S1 times P plus S2 times P squared, and then all the way until the end of the string. So for the case of this code, our base here is P equals 31, which is also a prime. And M here is 10 to the 9 plus 7 or plus 9, which is also a prime. And 1e is just 10, 10 to the 9. And then the hash value starts at 0, and our power P starts at 1. So technically, P to the 0 equals 1, so that's why it starts at 1. And then we go over every single character, and we update our hash value as we go along. So C here is still a char, but when we minus A, the character A, that assigns the value. Let's see. So in the ASCII table, the letters A to Z are in a continuous segment. So if you subtract the ASCII value of A, then the letter A becomes 0, the letter B becomes 1, and the letter Z becomes 25. And looking at this code, this only works for lowercase letters. But fortunately, you can generalize it to almost any character. And to do this, you basically just need to remove the part where it's C minus the character A plus 1. And instead, you just plug in the character itself. So you could just put in C there. And in C++, at least, it will auto-cast to an integer. And then we modulo M. And then every single time we update our power as well, because we'll be multiplying that as we go along. Okay, so that's the basic idea of polynomial hashing. And the pros of this is that it's very fast and it's also easy to code, because as you can see from this code, it's not too long and it's fairly straightforward to understand. And it's also very fast if you want to match strings together. However, the cons are that it's not 100% correct because it's not deterministic and there's chances of collisions. So if there's collisions, then your program will not work correctly, since it will be saying that two different strings are equal to each other, and we don't want that. So because of this, your code can be hacked, or in other words, it can be given a test case where it will provide the wrong output. Since there's nothing random about this code, it's very easy to just backtrack through the code and then come up with a case or two strings that will map to the same value. And that will break our code. So those are the pros and cons. And to minimize the chance of a collision, a lot of people do what is called double hashing. So a single hash has a 1 over 10 to the 9 chance of colliding. And that's assuming we take the modulo 10 to the 9. So essentially has a 1 over m chance of colliding, where m is the modulo. So double hashing is just hashing with two different bases and two different modulos. So the chance of colliding is just 1 over all the modulos multiplied together. So because of this, you can see that you could do triple hashing or even just hashing with 4 bases, but then your code gets very long and it's not that good. But at least in the case of competitive programming, where your test cases are often very specialized, so you just want to solve that problem specifically, then you can use single hashing or double hashing to quickly find or quickly match strings that will pass the test cases. But in a real world situation, it's probably not too good because it's not 100% correct, and you want things that work reliably. Okay, so now I can talk about rolling hash. And this is related to the Rabin-Karp algorithm. And the Rabin-Karp algorithm states that, or the idea is that we can find or we can match strings together by doing some arithmetic and multiplication to extract a substring out of a string and then match that with some other given string. So for example, if we had a string S and we had a substring of S, and we can call this S of L to R, and we want to match that string with a string T. So we want to check if those two are equal. Then if we subtract hash of R minus hash of L, and here we're defining hash as the hash from 0 to R and 0 to L, then you can see that we subtract the two polynomials and you'll get some section of the substring. So you get some section of the hash. That's not complete, but it will be the same length as T. Because if you're comparing two strings that aren't the same length, then of course they won't be equal. So here we're assuming that the length of S and length of T are the same. Or sorry, the length of the substring of S and the length of string T are the same. So after you subtract the hash of R minus hash of L, then we need to multiply the hash of T by a base to the power of L. So it's a little hard to show without a whiteboard, but let's take the case where we have S0 to S2, and we want to remove S1 and S0. Then you subtract S0 and S1 times P. So you're left with S2 times P squared. But if T was just S2, then we don't have the P squared. So that's why we have to multiply base to the L power, because that will raise everything inside T to the same power starting at whatever you're left with after subtracting the hash. So if you have any questions, you can just either unmute yourself or you can also put it in chat. And I would be very happy to answer that. So besides from just hashing strings, this is a little extra information, but you can also hash trees, and you can also hash numbers in a grid, and so on. So I won't get into too much detail in how to do this, but the idea for hashing trees is very similar. So you can do something like starting at the root of the tree, and then if you're going to a left child, you multiply by some base, and then you mod by some modulo. And if you're going to a right child, you can multiply by some other modulo, or multiply by some other base, and then mod by some other modulo. And hopefully that gives you a unique value. And if there's weights, then you can also factor that into your hash. So the method I went over about polynomial hashing, that's not the only way to hash, but generally that is one of the more conventional ways to hash. And it's very easy to find some substring of a string, given all the hashes that you pre-compute beforehand. Okay, so I think, yeah, so that is it for hashing. Okay, so I'll put out a poll and then we'll see if we can move on, or maybe I can really explain some stuff. Okay, looks like most people are good with the explanation. So if you wanted me to explain it again, you can just send me a private message if you're not too comfortable with putting it in chat. But I will, yeah, I would be very happy to help you individually or just re-explain it if you want. So just let me know. So we can move on from hashing now. The next topic I'll be talking about today is called the Knuth-Morris-Pratt algorithm. And this is also known as the KMP algorithm for string matching. And this is a very fast algorithm to search strings. And it's better than hashing for string searching because it's deterministic, while hashing is not. But based on what I explained before, hashing is really good for string matching, but it's not so good for string searching. And so the basis for the KMP algorithm lies in the prefix function. And we can define this function as an array, and let's call it P here. So we can call PI of string S as the maximum prefix of the substring starting from the beginning of S to index I. That is also a suffix of that same substring. That is not equal to the whole substring itself. So I put two examples here. We have S equals ABC, ABCD. And the first index is always 0 because there's no way that you can get a max prefix that is also a suffix that is not equal to itself because there's only one character. And then for the second character, it's AB, but then there is no prefix that is also a suffix in this case. And we keep going, ABC is also 0. But then when we reach the string ABCA, where I equals 3, then notice that A and A, so A is a prefix and A is also a suffix of the substring from index 0 to index 4, which is why the fourth number in P is 1. And then if we move on to ABC, AB, we get similar reasoning where the max prefix that is also a suffix of the substring is AB, AB. And the next one is ABC, ABC. And the last index is ABCD. But since it ends in a D, that's the only D that appears in the whole string. There's no prefix that matches the suffix, any suffix. So it's 0 for the last index again. Okay, and just in case anyone's still confused, the second example is similar reasoning, where A is 0 again. The first index is always 0. And then AA, we get 1, a length 1 as the max prefix. That's also a suffix. And then for AAA, we get AA as the max prefix. And it can't be AAA because that would be equal to the whole substring. Okay, and then we get 0 and 1, just filling out the rest of the prefix function in similar ways. So how do we build this prefix function? So you can notice that for every single pi, we can build off of pi minus 1, which is the answer before it. So first we can check the character at si and s of pi minus 1. Because pi minus 1 is the max prefix, that's also a suffix. So if we go back to a previous slide, let's say we're at the first example, ABC, ABCD, where we're looking at the first 6 characters. Then ABC would be the maximum one, while AB would be the maximum suffix, or the value of the prefix function for I minus 1. So we can just add a C to the suffix and prefix of the previous value, since they're the two strings match, or the two characters match. So you can just append them to both the prefix and the suffix, and you get a longer prefix value. So that's what we're doing in the second bullet point here. If the two characters are equal, then pi equals pi minus 1 plus 1. But if that doesn't work, so if the two characters aren't equal, then we have to find some other value. And it turns out that this value is equal to p of pi minus 1. So it's the longest prefix that is also a suffix of the longest prefix that is also a suffix of pi minus 1. So that might sound a little confusing. But what we're doing is we're taking the prefix that was also a suffix of the last of S0 to I minus 1. And we're taking the prefix function for that string instead. Because we know that that also exists in the substring 0 to I minus 1. So it might be easier to draw it out, but unfortunately, I don't have a picture right now. And there is a more detailed proof on why this is the case. But for now, I'll just leave it like this. And basically, we'll just repeat this step. So we'll keep setting p equal to, we'll keep setting our value to p of pi minus 1 recursively until either p of I minus 1 equals 0 or the next characters match. So here's the code for the prefix function. Hopefully it will clarify some confusion, if there's any confusion. So we first start with the prefix function. Here, we're going through every single character. And since the first index is always 0, we can just start from I equals 1 here. And then we first assign j equal to the prefix value of the previous index. And the while loop is the repetition that I explained in the previous slide, where as long as j, which is in this case p of I minus 1, so while that is greater than 0 and the two next characters do not match, then you just set it itself equal to the prefix function of its previous, like its previous longest prefix that's also a suffix. And then the if statement checks whether or not the two next characters are equal. And if they are, we increment j by 1 because we can just append those two characters to the prefix and the suffix. And then lastly, we update the prefix function for I. Okay. Yeah, so that's the code for the prefix function. And that's the underlying idea for KMP. And to use this prefix function, we can do the following. So let's say we have a problem that asks us to find all occurrences of string t inside string s. Then what we can do is we can define a new string, let's call it r, equals to s plus, I put a $sign here, and then plus t. So technically you don't need a $sign, but it should be a character that does not exist anywhere in t. And then after that, you can calculate the prefix function for this new string r. And lastly, we look at all the indexes inside our prefix function array, where pi equals to the length of s. Because what this means is that the longest prefix that is also a suffix of the substring 0 to I is of length s. But since the way we defined r tells us that the first s characters of this new string r is equal to s. Or sorry, wait, actually, I have a small typo. So it should be t plus $sign of s. Yeah, so it should be t and s should be flipped around. But the idea should be the same, where we're using the prefix function to tell or to find the location of all the occurrences by checking whether or not the prefix function value is equal to the length of t, because we put t in the beginning of r, string r. And that's why we put a character that does not exist in t or s, because that acts as a blocker. So it will never match anything in t or s. So your prefix function will never go over the length of t, because it will never match the $sign to anything. So that's how you use KMP in the case of finding all occurrences of string t inside a string s. And there are other applications of KMP as well. But for now, I'll just go over this classical problem of string matching or string finding. And this runs very fast. So calculating the prefix function is O of n, where n is the length of the string. And building the string is also in linear time. So the total time it takes to find all occurrences, and you can actually find the position of all occurrences. The total time will be done in linear time. So that's very, very fast. And it's also deterministic, which is a lot better than string hashing. So here is a further explanation on how we can use prefix function. So the example problem I put here is, let's say we want to calculate how many times a string t appears in S as a subsequence. So what I mean by subsequence, if you're not familiar with the term, is that it doesn't have to be a continuous sequence of letters, but as long as the letters appear in a certain order as t, then it counts as a subsequence. So let's say we have the word cow. So you have COW, then the word C or the word CW is a subsequence because C appears before W in cow. So we can use dynamic programming to solve this problem. And to speed up the DP, we can use the prefix function to optimize the transitions between these states. But I won't focus on the solution for this problem because that is more focused on dynamic programming. But if you're curious about it, I could explain it after finishing this presentation. So that's just an example of more uses of the prefix function. So it's a very powerful tool that can use to speed up or cache a lot of stuff, especially for strings. So notice that you can also do this for numbers. So it doesn't have to be characters as well. You can also do it for numbers and it would still work in exactly the same way. Okay, so it looks like we've reached the end of my presentation, but I'll launch the poll again in case anyone wants me to re-explain it. It looks like most people are okay with the explanation. So I can individually explain it again for the people who don't. But yeah, in the meantime, here's the attendance code. So it's hash KMP. And I will stop recording right now. But there is another Codeforce contest on Codeforces on the UCLA group that uses KMP and hashing. So some of the hashing problems are a little more difficult because they don't appear that much. So they're more on the difficult side. And if your program doesn't work for single hashing, that's probably because there's collisions. So maybe try double hashing in that case. But definitely check out the problem set. And I can re-explain KMP and hashing for the people who wanted me to re-explain.